Hi, I'm Michael Shannon, and in this course, I'll cover application and service level attacks. I think it's very appropriate to begin this course with the zero-day type of attack, this application and service attack that's almost an industry in itself. And we've heard about these 0 days, these exploits. Sometimes you see it as 2 words. Sometimes you see it as 1 word, 0 day. Sometimes you see it with a dash, 0-day. Regardless, these are unpublished exploits. Nobody really knows about them yet, or nobody knows about this variant of the malware. So your security software vendors, your IPS sensors, your firewalls, they're presently unaware. So as you can see in the diagram over here on the right, the attacker will create some unique special type of malicious PowerPoint slideshow with malware embedded. They'll send that attachment to targeted email addresses, part of maybe a spear phishing campaign or a watering hole campaign. The user opens the malicious PowerPoint slideshow and they become compromised, and hopefully within a few hours, companies like Kaspersky, Symantec, Sophos, Trend, and others will start figuring it out, but at that point it's a 0-day exploit. And there's an entire black market that creates these 0 days or selling the code. If you get a Tor browser and go into the dark web, you can find vendors who sell these 0 days. There's malware as a service where you could subscribe. Nation states have developed all kinds of 0-day attacks. The code is just sitting on each other's systems, either extracting and exfiltrating information as part of an exfil campaign, or waiting like a logic bomb to go off if, for example, the cyber war or World War C starts to escalate. So these are used quite a bit by state-based groups and organized crime. 0-day attacks will often leverage an exploit to push malware, spyware, adware, malvertisements, phishing email and attachments, or many other forms of malicious code, and almost always with a criminal or a malicious intent. As I mentioned, thousands of 0-day attacks or code are resident on systems all over the world. These 0 days are formulated by malicious coders when they realize that a company has released software but it has a vulnerability, for example, a new version of PowerPoint. The threat agent discovers the exploit either before the developer does, or it can strike before the developer patches the vulnerability. Attackers write and implement exploit code and possibly sell it to the highest bidder while that vulnerability is still open and available. And once the exploit's released, either the vendors or the public recognize it, or the developer often will catch it and generate a fix to stop what we call the cyber bleeding. A lot of these 0 days are aware of the vulnerability and are waiting for some future moment to unleash the exploit. In this video, you learned about 0-day attacks. Now, spoofing is not specifically categorized as an application or service attack. However, it is usually part of the early phases of an advanced persistent threat or a reconnaissance attack that's part of a campaign against an application or service. Spoofing is basically masquerading or posing as something that it's not. So it's really a technique to kind of use a bogus source IP address or redirect the ultimate target of the attack to a spoofed or bogus destination IP address. And again, spoofing can be done at other layers of the OSI model besides layer 3 with IP version 4 and IP version 6. Again, often part of the early phases of a external structured denial of service or flooding attack. The spoofed source address is often the ultimate target as devices perform return amplification. So for example, if I send an attack towards a web server or a DNS server or a router, it's going to generate a bunch of ICMP messages or TCP messages, and it's going to be amplified so that the number of messages sent from the pivot point, the router or the server, is going to be a lot more than what I sent to that actual device. And so the destination IP address is actually the target on some other domain. It could also be an external system masquerading as an internal system, or an internal system masquerading as an external system. So for example, somebody can be inside your organization, one of your employees, that's using an exploit kit, and they're masquerading their source IP address and using some script kiddie to spoof some address they got from the dark web, from a command and control service, or they're just making up some address that they found on the internet. Attackers can spoof a lot of things. We will see them spoof MAC addresses. That's commonly done in ARP cache poisoning attacks, DHCP spoofing attacks, or a rogue DHCP server in a wired or wireless network. If they can trick an endpoint into saying, I'm the IP and MAC address of your DHCP server, they can leverage that 8-bit options field in the DHCP packet to reconfigure those clients to point to them for a wide variety of things. Their NTP server, their name server, their default gateway, a wide variety of options. Routers can also be spoofed. Somebody who gets inside your organization can spoof neighbor or peer routers and then corrupt routing tables, which will eventually corrupt the data plane and the traffic forwarding through those routers. In the dark web, you can go and purchase entire spoofed domains and URLs. Some of the services will allow you to pay them a certain amount of money and you get a year's supply of domains and URLs. And of course, spoofed websites. A spoofed website that leverages DNS is what we call farming. And of course, spoofing email addresses happens with phishing, spear phishing, and whaling attacks. In this video, you learned about spoofing as it relates to application and service attacks. Denial of service or DOS attacks are some of the oldest exploits that were designed to leverage the inherent weaknesses in the TCP and IP protocol stack. Realize in the RFCs, when they developed these protocols, they were made to encourage and enhance and facilitate communication of hosts between internetworks. And so instead of rewriting the actual RFCs and changing the protocols, which would have obviously thwarted the advantages of that interoperability and that interconnection capability, they found other techniques that were in RFCs to help deal with some of these problems. For example, special types of access control lists, anti-spoofing ACLs that would be applied to layer 3 devices to accommodate for some of these attacks, and also Unix boxes that were running early versions of firewall services and IP filtering services. The denial of service attack, its goal is to basically consume an individual system or an entire network's critical resources, like using up disk space, taking CPU cycles from the device, filling up memory addresses, or it could be the content addressable memory on a switch, for example, using up network bandwidth, overloading the input queue on a layer 3 device. You can do a denial of service attack against a DHCP server. It's called DHCP starvation, where you kind of you flood it with a bunch of requests from bogus MAC addresses, and you use up the leases on that DHCP server, and then that server can no longer respond to the DORA process, the DORA, and then you can put in there your rogue DHCP server or perform some other man-in-the-middle attack. Denial of service attacks are still common. They're constantly bombarding service providers. Often they'll just throw more bandwidth at it as opposed to trying to countermeasure it. But a lot of corporate servers are constantly under attack from denial of service attacks. They're easy to launch, and there's a bunch of exploit kits and modules and Metasploit and Kali Linux and others that can give you graphical interfaces to construct all different types of denial of service and flooding attacks. Here we see a classic denial of service attack. It's always kind of good to go back in history and look at what was done early on. This is the TCP SYN flood attack. Now what we see here, this is actually showing that this is part of a botnet. That would actually be a distributed or a DDoS attack let's don't go there yet, okay? We'll go ahead and use this diagram to do our traditional denial of service attacks. I'll just scratch that out right there. But here's our hacker over here, okay? Our black hat hacker. They're going to exploit the TCP three-way handshake, okay? So when this system, let's say, is going to connect to a server up here, let's say a web server, HTTP is going to be TCP based, so there's a three-way handshake that's going to take place at the outset. So it's going to send random source addresses, okay? And by the way, it can get those random addresses on the dark web. It sends these spoofed SYN packets, usually a bunch of them. The server here will then send SYN-ACK, or synchronization acknowledgments, and it's sending them back to the source address. But remember, the hacker over here is not actually at the source address that was in these spoofed packets. They're going somewhere else. Now, sometimes the target, it's an amplification where they're sending a bunch of these, and the target is actually the source of their attack. So that's actually who this hacker is ultimately trying to attack, and he's using this web server as kind of a pivot point. So this three-way handshake is never completed, and these will stay inside the connection table on this server until their timer expires, which could be quite long. You do enough of these at a rapid rate, and the attacker can fill up the connection table. They can deny TCP services that server is trying to provide, web services, email services, file transfers, so it affects legitimate users. And because that source IP address was forged, and probably because this attacker is using a Tor browser, hiding in the deep web or the dark web, we'll never find the originator of that attack. And this technique, let me clear the screen here. Now we can talk botnet. In a distributed DOS attack, this technique is still commonly used. The botnet will use malformed SNMP packets, syslog messages, DNS, and other UDP-based protocol messages. So you can flood with TCP and UDP packets. In the old days, we used to call this the ping of death, where you would use ICMP and you would just use one of the variables in the echo request or the ping and have, a huge number of requests sent. And so it would overwhelm that target with ICMP messages. That's not really done much anymore. However, more recently we've seen an IPv6 ping of death, which is a variant on the original IP version 4 ping of death. Those crackers are very clever. In a DDoS attack, a distributed denial of service attack, it's going to involve malicious zombified hosts, okay? As many as possible. They can combine to flood a victim with many attack packets simultaneously from potentially thousands of source IP addresses. This attack is often sourced from networks of compromised systems called botnets. A botnet consists of a group of systems loaded with computer robot code or bots. Remember, botnets can be part of a DDoS attack where you're obviously attacking a target, or the botnet is silently, in a stealth fashion, sitting there and performing activities on the end user's system without them knowing that. So, a distributed DOS attack can be something that is going to, do denying of services, but in a way it can also be used to force a host to do services that it's not intended to do, or that the owner of that system, the custodian of that system, doesn't want it to do. So, these definitions have expanded as the malware gets more creative. A command and control server, or what we call a C2 server, is typically, I won't say typically, but often it's other parts of the world, maybe Eastern Europe or Asia, on the dark web, and it's directing the zombie computers remotely, often using the IRC service, Internet Relay Chat, peer-to-peer functionality, or we've even seen Twitter being used as part of a DDoS botnet attack. So here we see the attacker over on the left-hand side, sitting behind a Tor browser somewhere in the deep web or the dark web. The command and control server may be their server. It may be, some cloud service they're subscribing to, or they may be part of some syndicate. They may be working for a government, and that's the command and control server. The C2 server can be owned by a wide variety of actors and threat agents. So the operator of the botnet is going to infect computers by sending them malicious bots, which is self-propagating malware, a worm-like ability to self-propagate. And it can do all kinds of things, like I've said. Gather financial information, credit cards, keystroke logging, passwords, analyzing packets. It can further launch denial of service attacks. It could do relay spam. It can open back doors. Remember, this is really just the delivery system. This is the infrastructure for delivering the payload. The malware itself can be a single type of attack, or it could be multi-phased, polymorphic. And again, often the command and control server, the C2 server, is an IRC server or even a web server. In this video, we explored DOS and distributed denial of service attacks as it relates to application and service attacks. Remember, man in the middle is not always an attack. Sometimes a man in the middle or meat in the middle is a proxy, a good thing. It could be a translation proxy or an encryption proxy, an application layer gateway, but a lot of times it's dangerous. It's a proxy ARP attack. It's used for DHCP spoofing. It's somebody interjecting themselves into a TCP connection, leveraging the window size, injecting malicious traffic, or possibly capturing information as a man in the middle. So it's a system that has the ability to view and communicate between two or more hosts, at layer 2 with frames, at layer 3 with packets, injecting itself in the path between the two host systems. These are complex attacks. They can either be what we call simplex, which is kind of a one-way delivery of payload, or they can be duplex attacks, where there's actually kind of a TCP communication sent back to the man-in-the-middle attacker. And again, they can happen at different layers of the OSI model. Here we see the proxy ARP attack, the attacker at 10.1.1.5. Let's say they've installed Kali Linux, or they're running Kali Linux off of a USB flash drive, plug it into their workstation or their laptop, and they basically are going to trick or poison host A and host B at 10.1.1.4. So the attacker is going to tell host A that host B's MAC address is themselves, and then tell host B that host A's address is themselves. And this is a attack that's very easy to do. There's scripts, there's modules. It's not that hard to mitigate against this. You can do some static ARP entries on this switch here. We can do some port security on these switches as well. We can hard code MAC addresses, or we can sticky learn the actual MAC addresses. There's other features that we can implement. We can create a binding table. If we're using DHCP, we can create a binding table that will bind the actual MAC address of the interface to an IP address and its VLAN membership. And then we can use that binding table to enforce other services like dynamic ARP inspection and IP source guard to make sure that this attacker cannot send illegitimate information at layer 3 or layer 4. In this video, you learned about man-in-the-middle attacks. In this short video, I want to return to the concept of the ARP poisoning or ARP cache attack, which is really a subset or a form of man-in-the-middle attack that exploits ARP. This attack is only going to be a vulnerability found in IP version 4 because IP version 6 no longer uses ARP. It uses additional ICMP version 6 message types to perform the same functionality. With ARP poisoning, the malicious host will inject false frames, often using a GARP, a gratuitous ARP message, to corrupt or poison the ARP cache buffers on endpoints, on switches, on servers, and even firewalls and routers. All of those devices use frames. This is an IP version 4 attack, and there's a bunch of exploit kits. I'd say all of them have several scripts and modules and tools that can be used to compromise the ARP protocol. One of the first to really excel at this was the Metasploit kit. You can mitigate ARP poisoning, as I mentioned in a previous video, by having solid port security or just having best practices when you configure your access switches from the outset. But you can also build these snooping binding databases. You can implement 802.1x port-based authentication. You could even do MACsec, which is 802.1ae, which will actually optionally encrypt and apply an HMAC to the frames themselves, between the host and the switch, or between the switches in your switch fabric. In this short video, we talked about ARP poisoning. In this video, we're going to look at buffer overflow attacks, and you're probably noticing a theme here as we talk about service and application attacks. We're really talking more about the vectors that are being used or the delivery systems that are being used, the frameworks, not so much the malware. All of these different types of quote-unquote attacks can deliver a wide array of different types of malware and structured, multi-phased, multi-step attacks, polymorphic viruses and worms. So we're really talking about an exploit in a buffer overflow attack that's finding a flaw in an application, a software, an operating system, either when it was initially coded, its design, and or deployment. So let's say you have a service that expects a certain input, and it needs to be within a certain window size to be written to memory addresses, but it doesn't verify that. Well, that code may be vulnerable to a buffer overflow attack. The attacker who finds this flaw will then send larger than expected input. For example, a web server accepts this and writes it to its memory. The associated buffers will get filled and adjacent memory is overwritten as a result. And so the code that is overriding those memory addresses, those memory slots, may actually contain malicious code or instructions or executables that can crash the server at the very least, resulting in a denial of service attack. But the code can actually be much more malicious and be part of a DDoS attack, which can spread to other systems. Buffer overflows are common vectors for client-side attacks. Here's an example. A hacker, a malicious hacker, posts an infected file on a web server, and then an unwary user downloads the file and opens it in a vulnerable application. This will spawn malware that connects to other rogue servers on the internet and then downloads additional dangerous payloads. That cracker is just sitting there hoping that that drive-by download will infect a system that's vulnerable to this particular buffer overflow. Vendors like Microsoft are constantly sending out patches and updates to mitigate buffer overflow exploits. As a matter of fact, sometimes the software developers and the operating system developers will just use the public as their alpha and beta testers, knowing that there's going to be vulnerabilities there, and they just kind of get the code out there, they get the application out there, and they're just ready to patch and update and provide service patches and security fixes on an ad hoc basis. Basically because the motivation to get the product out to market outweighs writing perfect secure code. And so it's really the way that it's really a risk management, a risk handling decision made by these vendors. But to wrap up, one of the most common threat vectors or delivery systems is the buffer overflow attack. Let's talk about injection attacks. An injection attack is often delivered using the vector of a man-in-the-middle scenario or possibly a buffer overflow. And commonly today, the payload is a RAT, a remote access Trojan, and that Trojan will either do exfil from memory or something like keystroke logging or some other information to get passwords and credentials and PII, but it's also going to place a payload that's a launching point for additional botnet or DDoS activities. It can inject false MAC addresses. It can inject false IP addresses. A SQL and SQL injection attack is a very common attack against, let's say, Apache and IIS web servers that are using SQL as their back end. They're probably storing information in the database on the back end, like, for example, password hashes, credit card information. And so you can inject in the URI of the web-based client SQL commands that can go and request part of the database from tables. As a matter of fact, some of the trends out there are to use things like NoSQL, for example, for backends to web servers that are not subject or not vulnerable to these types of SQL commands that are injected in URIs and URLs. Exploit kits, like Loki, can inject bad information and give it to routers and inject that into their routing tables. If those routers are not authenticating their peers, if they're not using route filtering, then they're going to be vulnerable to these types of tools, both externally and internally. Also, STP information can be injected on switches by spoofing the bridge protocol data units. So if you're not using things like BPD UGuard and RootGuard and other layer 2 security mechanisms, then spanning tree protocol can be vulnerable to injection attacks. So, just remember, an injection attack is just a general term for a threat vector or a delivery system that has the capability to inject false information to an application, to a protocol, to a service for malicious purposes. Privilege escalation is actually considered a category of attack, but realistically, it's one of the phases, it's one of the steps in a structured or advanced persistent threat. It is a phase where you try to escalate your privileges from normal user privileges or lower level privileges soon after the initial compromise. The cracker's goal is to become a root user, like on Unix or Linux, or an administrative user or a member of, let's say, a global admins, enterprise admins group in a Windows directory, some type of level 15 user in a command line interface in the Cisco iOS or the Junos operating system. In other words, going to a higher level so you have greater authorization on that system or multiple systems. The higher the level, the broader the access, and the more potential there is to damage other systems or exfiltrate critical data. Organizations that have a good security policy will have a least privilege principle, where typically a user will log in with a regular user account and then only use the admin privileges on an as-needed basis. They'll also have architectures like the common criteria. They'll use mandatory access controls, discretionary access controls, role-based access controls, different architectures to provide access level security. The goal of privilege escalation is to exploit a flaw or a bug in the authentication, authorization, and accounting system in its design, or possibly some access control configuration error. The goal can be exploiting a vulnerability in an operating system or the application running in the operating system. There is vertical escalation and there's horizontal escalation. Vertical privilege escalation is also known as privilege elevation. And this is where a lower privilege user or application will access a function or data that's reserved for higher level users or applications. So for example, let's say you have users that are using online banking. They could actually escalate access to get site administrative functionality. Or maybe they can, bypass the smartphone password to get elevated privileges. That would be vertical. Horizontal escalation is where a normal user would access the function or data of another normal user on their same level. So online banking user X accesses the information of online banking user Y. Another example, some Windows services are configured to run under the local system user account, and a buffer overflow would execute arbitrary code with privileges elevated to the local system. In this video, I'm going to talk about reflection attacks and amplification attacks, which have kind of reared their ugly head again in IP version 6. We kind of got a handle on them in IP version 4 with a lot of different countermeasures and firewall features and just understanding the way that ICMP and other protocols were being used. But again, in IPv6, we've got some new vulnerabilities. The bottom line is reflection attacks and amplification attacks are closely related to denial of service and flooding, where an attacker sends a flood of protocol request packets to various hosts. The attacker will typically spoof the source IP address of the packets so that it's actually the IP address of the anticipated target. Hosts that receive these packets become reflectors or pivot points when they reply by sending response packets to the spoofed address, which is the unsuspecting target. If the request packets, for example ICMP or DNS or SNMP, solicit a larger response, the attack also becomes an amplification attack because a small forged packet provokes a much larger reply from the reflectors or the pivot points. Reflection and amplification are two separate elements of the attack. In other words, all amplification attacks are reflection attacks, but not all reflection leads to amplification. Attackers can use amplification with a single reflector or multiple reflectors, as in IPv6 amplification. Some of the common points of reflection and amplification would be edge routers, edge firewalls, servers that are in a DMZ, for example. Basically any device that has an interface on the public internet. Here we see kind of the classic ICMP Smurf attack. So basically over here we have the attacker who's going to send ICMP echo requests, and they're going to send it to this router here, which is going to be our pivot point or reflector. And they're going to have in the source IP address 209.165.1.5, which is actually the victim down here. So this attacker on this slow connection sends this echo request, a flood of them, to this router, which happens to be on a high bandwidth Metro Ethernet connection. And of course, this becomes a reflection point, sending it over this T1 connection to the victim down here. Thousands of ICMP echo replies to 209.165.1.5. And again, a wide variety of protocols can be used for reflection amplification. It can be TCP based, but it's usually UDP based or ICMP. And again, this is another emerging issue with IP version 6. In this video, we talked about reflection and amplification. Well, as you're learning, a lot of things can be poisoned, okay? Poisoned by malicious attackers using script kiddies and modules and kits. DNS is among those things that can be poisoned. Basically, the name resolution information is changed that should be in the DNS server's cache so that the client systems are redirected to incorrect websites. This is also known as pharming, P-H-A-R-M-I-N-G, where the attacker will have a bogus or mocked up website that looks just like a brokerage firm or a bank, but it's not. This is accomplished by name server misconfiguration, and proper software design can also lead to this, and malicious exploits that are designed specifically for the DNS system. For example, you want to go to www.CompTIA.org. Your DNS server will have a cache of domain name information and their matching IP address. If this site was recently visited by any client accessing the DNS server, the information should be in the DNS server's cache. When a cache is poisoned, however, it's often changed to redirect request for a domain to a different address and website. This other site could be performing phishing, pharming, or some other drive-by malware malicious activity. In this short video, you learned about DNS poisoning. In this video, we're going to review a topic that we've talked about in other areas of this learning. And don't worry, the gun's not loaded, okay? Domain hijacking. Domain hijacking is basically when malicious users set up methodologies on websites to redirect client users and browsers to other areas on the internet. And what they'll typically do is they'll take advantage of mistyped input in the URL bar. Maybe they're being redirected through spam or phishing attacks. It could even be banners or icons or other links that are placed on websites to redirect them away from the real site to a fake site. Other names for domain hijacking are cyber squatting, brand jacking, direct linking, typo squatting, sting sites, and fake URL. In this short video, I reminded you of domain hijacking. A man-in-the-browser attack is a specific form of man-in-the-middle attack where you're leveraging HTTP or even HTTPS, which would be using SSL TLS. The man-in-the-browser attack uses the same tactics except that a Trojan horse malware program is used to capture and manipulate calls between the main browser and security mechanisms or libraries, and it's done on an ad hoc basis. The most common usage is financial fraud, where we're manipulating transactions of internet banking and commonly used brokerage sites. And it can work even when other authentication factors are being used. In this diagram, we see that on the far left-hand side, a laptop that's going to do their online banking and they log in as normal. At the top, they use their password, but the site has been compromised. So there's malware on the web server that actually captures the information and makes transactions in the background. And of course, those transactions are obviously unauthorized. Down below, the login has a secure key, but the user is tricked with some interface into using a device to generate a passcode. That passcode is taken, they click on a link, then the malware on the web server uses that information to perform an unauthorized or illegal transaction against the banking site or the brokerage site. In this video, you learned about the man-in-the-browser malware attack. In this video, we're going to discuss cross-site scripting, which is XSS, and cross-site request forgery, which is XSRF. I got quite a few bullet points here because we have to really describe these very well. They're very prevalent attacks against websites, client and server side, and I don't really have any good other way to kind of show how this works other than just using kind of a text description. So these are probably the most common attacks, okay? Cross-site scripting is an exploit that uses a type of code injection that takes advantage of web programming flaws or bugs by inserting and processing invalid data. So in essence, it modifies how the program executes data. With a cross-site scripting attack, malicious scripts are inserted into a web page. Then they try to get escalated privileges as well as access session cookies and other data that's stored by the user's web browser. They often happen when JavaScript code is injected from a separate attack website. It can also occur as an embedded JavaScript image tag or some other HTML embedded image object in webmail. The cross-site scripting attack can be defeated by preventing the use of HTML tags and by doing solid input validation. That's the key. This includes checking web input forms and confirming that user input doesn't contain hypertext. On the client side, increasing cookie security and disabling scripts can be used as countermeasures. If XSS attacks by email are a real concern, then the user can choose to set his email client to text only, which in some government organizations, some high security environments, that's what they use, text-only email. The cross-site request forgery attack exploits the trust that a website has in a user's browser. This is also known as a one-click attack. The user's browser gets compromised, and then consequently, it sends unauthorized commands to the website. Countermeasures to XSRF would be requiring tokens on web pages that contain forms, special authentication mechanisms, using TLS encryption, having web security that scans XML files, and submitting cookies twice instead of once, while verifying that both cookie submissions match. I want to suggest to you that you take some extra time to go and research web server security and web server vulnerabilities like these two attacks. They won't be covered deeply on the exam, but from a real-world standpoint, web security is a huge deal because so much percentage of our traffic is web-based. So take some time on your own to build up your knowledge base for web-specific attacks like cross-site scripting, cross-site request forgery, SQL injection attacks, and other types of malware directed specifically towards web servers. In this video, we're going to explore replay attacks, which is really a broad category of types of attacks that are done in internetworking. A common replay attack that involves cryptography is where two identical plaintext blocks are encrypted using the same key. Then their ciphertext blocks are the same, so the attacker can identify similar or identical traffic flowing through a communication channel and then use this information. They could build a catalog of messages which have a certain meaning and replay them later without even knowing the real meaning. An example, attacker might capture a login sequence of someone with administrative privileges whose traffic is protected by DES ECB and then replay it. S-MIME is a tool to use to ensure confidentiality and integrity of email messages that are subject to replay attacks. When both authentication and encryption are selected, encryption is performed first. One reason for this order of processing is that it facilitates rapid detection and rejection of replayed packets or bogus packets by the receiving device. Before decrypting the packet, the receiver can authenticate inbound packets. By doing this type of authentication, it can quickly detect problems and potentially reduce the impact of denial of service replay attacks. IPsec provides anti-replay mechanisms built into the protocol. Anti-replay protection verifies that each packet is unique and is not duplicated. IPsec packets are protected by comparing the sequence number of the received packets with a sliding window on the destination host or security gateway. A packet that has a sequence number that comes before the sliding window is considered either late or a duplicate packet. Late and duplicate packets are going to be dropped. In this video, we talked about replay attacks, which are very common when cryptography is involved. Let's talk about the pass the hash attack, which is pretty common on Windows networks, where hackers don't need the plaintext passwords to access certain services. Sometimes the authentication process relies on the password's cryptographic hash, and there's various tools to extract these hashes, like Cain or John the Ripper, from compromised Windows machines. And this has happened lately on Windows 10, and it uses them to access other services. This technique is known as pass the hash. Try saying that 4 times fast. And it's one of the attacks that Windows Virtual Secure Module, VSM, was intended to protect against. The Windows Safe Mode on any version of Windows is vulnerable to this type of attack. Safe Mode's an OS diagnostic mode of operation that's been around since Windows 95, and it can be initiated at boot time and only loads the nominal set of drivers and services that Windows needs to run. Most third-party security products don't start up in safe mode. In this video, you learned about pass the hash attacks. Okay, it's time for an exercise, and in this one, we're going to give you 3 tasks. And I'm going to give you the task. I'd like you to go ahead and pause the video, document the task some way that's convenient for you. Go get the answers, and then come back and we'll compare our answers. Here's your 3 tasks. First, list 3 protocols or services that can be spoofed. Second, name a tool in Kali Linux that can perform injection. And then third, list the 2 most common attacks targeting web servers. Pause the video and perform the exercise. First, I ask you to list 3 protocols that can be spoofed. If you said any 3 of these, MAC addresses, IP addresses, DHCP, ARP, routers, domains, URLs, websites, or email addresses, then you got the correct answer. Next, I ask for a tool in Kali Linux that can perform injection. If you said Loki, L-O-K-I, you got the correct answer. Then I said list the 2 most common attacks targeting web servers. From this particular course, you could have really said any of 3 things: cross-site scripting, XSS, cross-site request forgery, XSRF, or you could have said SQL injection, and that would have been a right answer as well. All right, good job.